All right, so we're going to go through quite a few of the problems from the negation introduction worksheet, both because I don't have time to do them all in class and also because they're really a great way to consolidate your understanding of the material we've gone through so far. So let's start with number 4 from the worksheet. Now, I may have done this in class already, and the solution I'll offer here might be different than the one I did in class, so don't get freaked out about that. There are a lot of different ways to do things, and it's good to experience them. So here we're asked to, you'll notice we're asked to derive a conjunction, not S and R. So go ahead all the time, stop this at any point where you think you can advance the proof on your own, or you want some time to think through it before I say anything. So please don't just watch this develop and con yourself into thinking you're understanding it. Okay, so we've got a conjunction, not S and R, that we need to derive. And we also see that we are probably going to have to derive it from a disjunction. Now, at this point, you should be thinking, if I've got to derive something from a disjunction, there's just a really good chance I'm going to have to use disjunction elimination. So one thing that you could imagine yourself doing is assuming not S, hypothesizing not S, and deriving not S and R, and then hypothesizing not P and deriving not S and R. And that would work. That'll work just fine. But if you look at it a little bit longer, you'll see that you have P and if P then R, which immediately gives you R by conditional elimination. So you could just go ahead and write that. And then focus on just getting not S from the disjunction. So then you would go, look, let's first get if not S, then not S, which is that funny little quick move. And then let's go ahead and get if not P, then not S. So let's try that. Let's hypothesize for a conditional introduction, not S. And now, well, we're trying to get not S. So if not S, then not S goes, as we've seen in class, in one move, right? If you have not S, then you have not S. So that's 6 through 6 conditional introduction, and go ahead and drop your line. And now what you want to do is get your second conditional, if not P, then not S. So go ahead and hypothesize not P. And now you want to try to get not S again. Now, there's no, if you look at this for a while, turn me off, look at this for a while, you'll see that there is really no move that we have that would just generate not S. And so when you're stymied that way, the thing to do is, well, think maybe I need to do a hypothesis for negation introduction. So since you're trying to get not S, what you want to do is hypothesize S. So you've got 2 hypotheses in a row, one for conditional introduction, one for negation introduction. And now, anytime you create a hypothesis, you're changing your task, right? So now you've hypothesized S. And so what you are looking for now is a contradiction. Now, a rookie mistake here would be to say, oh, S and not S, right? But remember, this not S is not available to you anymore because we've dropped a line here. So you want to look a little bit closer. And when you do, you'll see you've got not P and P, right? So that's the contradiction you're going to want to write down on line 10 by hand introduction on 1 and 8. So you got your contradiction. Since you've got your contradiction, you've fulfilled your task, and now you can write the negation of the hypothesis, which is not S. So 9 through 10, negation introduction, drop your line again. Okay, so now just sort of stop and take stock. What have you achieved here? You've got if not P, then not S. So you've gotten rid of, you can now discharge your hypothesis for conditional introduction, right? If not P, then not S, and drop your line by 8 through 11 and conditional introduction. And so now you see that you have created both of the desired conditionals, right? So now what are you entitled to do? Well, by disjunction elimination on 2, 7, and 12, you're entitled to write not S by disjunction elimination. So now you've got R and you've got not S, and you can just put them together by 2 and 13. Excuse me, by 4 and 13. 4 and 13 and introduction. Okay, so that's the first one. All right, so on number 5, again, we are asked to prove something from a disjunction, and specifically you're being asked to prove a negated conjunction. Only one assumption here. And this, since the negated conjunction is sort of locked up by this negation, it looks pretty clear that what you're going to have to use is disjunction elimination. So it looks like you're going to have to demonstrate, looks like you're going to have to show that if not P, then it's not the case that P and R. And then afterwards show if not R, then it's not the case that P and R. Okay, so if you try to do that, you'll begin by hypothesizing not P, and now you're looking for not P and R. But really, it doesn't look like there's any way to get that from not P. I mean, if you had not R sitting there, you could add it in. Excuse me, if you had, well, actually, scratch that. I mean, there's just no way to do it. So you could give up, or you could say, well, maybe I could get some value out of negated introduction. So if I wanted to do that, I would hypothesize the opposite of what I want to derive, which in this case is P and R. So I'll just hypothesize. I want to hypothesize P and R because I'm trying to derive it's not the case that P and R. And now things are looking up, right? Because anytime you hypothesize for a negated introduction, what you want is a contradiction, and you can see the beginnings of a contradiction right here between not P and P. So if you put P on a line by itself by and elimination, you can immediately write P and not P. So you got your contradiction, which entitles you to do what? Well, it entitles you to assert the negation of your hypothesis. So now you can assert not P and R, taking away the indent and dropping a line. So you've got your conditional introduction now, right? You've got if not P, then not P and R. So go ahead and assert that by lines 2 through 6, conditional introduction, and drop a line. All right, so you've got your first one. Then just do the second one. Now the second one works exactly the same way, so you should really just stop this and do it yourself and check back later. All right? Okay, it's now later. Not R, P and R, right? So not R for conditional introduction, P and R for negation introduction. Again, R by 9 and elimination. Now, notice don't make any weird mistakes like going up here and getting R, because that's not available anymore. Nothing behind this line or this line is available. All right, so you've got R and not R by 8 and 10 and introduction, which allows you once again to assert the negation of your hypothesis, dropping a line, and then asserting again your conditional. So exactly the same set of moves, except with the other conditional. And now you got them both. So by 1, 7, and 13, and your powerful rule of disjunction elimination, you've got this done. All right, number 8 is one of the first ones we encounter that is really just plain old difficult, and it's irritating that it's difficult because it doesn't look like it ought to be. Now, what makes this difficult is kind of cool. It's that it really requires some creativity, and this is something you haven't really encountered yet, even though this is not an entirely mechanical process. Natural deduction isn't. For the most part, we've just been applying the rules and learning the rules in a pretty straightforward manner. But here, you actually have to sort of come up with ideas and try things. So if you figure this one out on your own, that's great. If you didn't, don't worry. And see if you can hang with me in understanding how this one works, because we're going to see some other ones that are as challenging in the same way. So this says that we should be able to get T or not S from if S then T. And if you think about this, you know that that's right? Because go back to the refutation tree rules, right? That if S then T goes to not S or T, right? That's an or. So not S or T, and you know that not S or T is logically equivalent to T or not S. So we know that we should be able to do this. We're not doing refutation trees, but it's useful to go back and think about refutation trees sometimes and what they allow you to infer. Okay, so what we need to do, it looks like, since it doesn't look like, again, you might have desperately tried to do a conditional introduction proof, but of course what you would have been doing there is trying to prove your assumption, right, which is not something you do. It's sort of the weird reverse thing, right? I mean, it would have been simple to go from T or not S to is F then T, but we're being asked to go the other way. So the simple, straightforward move, first of all, is just to go ahead and hypothesize the negation of the conclusion. That's what you do when you don't know what else to do. So we're in a negation introduction proof now. Now, the problem is that, what do you do now? I mean, it's not clear that there's anything you could do at all. So what do you do in a case like this? Well, the answer essentially is that you have to strategically try to negate something in particular, right? So you might say, is there some way that I can try to construct the proposition it's not the case that if S then T? So you could try to do that. Is there some way I could try to construct it's not the case that if S then T? Or alternatively, you could say, is there some way I could try to construct T or not S? Could I try to construct T or not S? Now, disjunctions are a little more promising in this way because, well, if you get one of them, you can just add in the other, right? So what if he just said, I'm going to try to construct T or not S. I want to try to make T or not S. And what you could do if you want to try to make T or not S is to try to make T, or alternatively, try to make not S. Right? You could do either one. And then hopefully add in the other one if you were successful in doing that. So what would you do if you wanted to make T? You know, how do I make T? How do I make T? Well, how about hypothesize not T, right? Now, there's no guarantee this is going to work. Well, it is going to work because I did it already. But while you're doing this, you're just kind of exploring, and you're probably going to have to go back and try something else. But suppose I hypothesize not T. Well, what good is that? It's not clear that it's good for anything. But what I can see is, dang it, if I had S, right? If I had S, I would be able to have T, and that would produce a contradiction. And so, well, that's interesting, right? Because that means that I can actually go ahead and show that not S, right? Because if you have S, then you have T, and you've got a contradiction. So what you can do here is go ahead and hypothesize S. Go ahead and hypothesize again. So isn't this is whacked, right? You got 3 hypotheses in a row for negation introduction. But it's cool. There's nothing here that we've done wrong. And just hang in there and see what happens, right? Now we've got T, unsurprisingly, by 1, 4, and conditional elimination. And now we've legitimately got our contradiction, T and not T. But what it contradicts is the last hypothesis, which is S. So now we've actually shown not S on the basis of not T, right? So we've got 4 through 6 negation introduction, and now we've got not S. Now what good is that, you ask? Well, because remember, now we're still just stuck doing this negation introduction, so we still need a contradiction. Where is that going to come from? We'll stare at it for a few minutes. Turn me off and stare at this for a few seconds or minutes and see if you can see where you could get a contradiction now. Okay, well, did you see that? You can contradict that very assumption. You can contradict not T or not S, which is what we were trying to do, right? So you can add in T by disjunctive introduction on 7, and then assert the contradiction, and now you have not T, right? You can assert the negation of that hypothesis. Now, of course, what you actually want is T, right? But remember, you're still in another hypothesis for negation introduction, but now you can see that you can do the same thing, right? T or not S by 11 in or introduction, and exactly the same move, contradiction between 2 and 12, and that allows you to assert the negation of the original hypothesis, and voila. Now, I just want you to know that this is the kind of proof that I would not put on a timed test, because it really, there's just no telling how long it would take you to come up with a strategy here. But the more you work on proofs like these, the truth is the easier the other ones become. So you should really try to work hard on this proof, be able to understand it, generate it. And then later on next week, we'll be looking at some other ones that have the same flavor. All right, number 9. This is kind of really a garden variety proof that you probably aren't going to have a whole lot of trouble with. Take some time to do this. So we've just got S and R and then 2 conditionals that are interestingly, one has the consequent Q and the other has the consequent not Q. Now you'll notice that P is not represented here at all, right? So that's weird, and that makes it seem like we're going to have to get some value out of this apparent contradiction to do what we know we can do, which is that once we have a contradiction, we can prove anything we like, right? So how are we going to do this? Well, take some time to try on your own, but clearly we've got S and R free and clear, right? S is going to give you S or M. R is going to give you R or L. So we have the antecedents to both of these, so we've got Q and not Q, right? So you should be able to take that on your own. Go ahead and shut me down and build all these hypotheses. So we've got Q and we've got not Q by a very straightforward set of inferences. And, well, what good is that? We're trying to get P after all. And you could have hypothesized not P earlier. That would have worked just fine. But you can also do it anytime you want. So you can just hypothesize not P now. Now, what do you want? Why did you do that? Well, it's for a negation introduction. What do you want now? A contradiction? Well, that's nice because it's sitting there on 6, 9. So you just put those together and then you can infer the negation of the hypothesis, not P, drop a line, P, 12, and negation, elimination. All right. All right. Here's the last proof. This last one is challenging only in the sense that it involves a huge amount of bookkeeping, because what you have here is a disjunction, right? And a disjunction of a disjunction and an atomic proposition. And if you did this, what you ended up discovering is that you do a disjunction elimination, but then you do another disjunction elimination within that disjunction elimination, right? So you're going to have to do a disjunction elimination for the big disjunction and then a disjunction elimination for the little disjunction. There's nothing conceptually difficult about this. It's just a lot of lines and a lot of indentations and a lot of hypotheses. So let's see how this works. Well, notice that what you're trying to prove is a conditional, and it's a conditional with the consequent as a conditional. So from your knowledge of proving conditionals, you know that what you want to do is hypothesize not S for the purpose of deriving if not M then N, and then hypothesize not M for the purpose of deriving N, right? So again, these two hypotheses are just going to sit here till we come back and get them later, right? But really what we want to do now is derive n, right? So first we have to show if m or n, then n. And then we're going to have to show if s, then n, right? That's what we need to do. But as I was saying before, right, so you go ahead and hypothesize m or n. Well, that's great, but that just gets you another disjunction, right? Well, that means you're going to have to show if m, then n, right? If m, then n, and you're also going to have to show if n, then n. So that's the structure of the proof. So you're going to start, so we've already got 3 hypotheses. These 2, remember, are just sitting there. They're not going to be involved until the end. But now you're going to hypothesize m, and from m, you're going to try to get n. Well, how are you going to do that? Give it a shot. You should be able to figure this out, but it's not just being handed to you, right? Well, you've got a contradiction, right? You can, in m and not m, right? You've got a contradiction here. So go ahead and hypothesize 1, 2, 3, 4, 5 hypotheses. Hypothesize not n. Write down your contradiction, and you can conclude the negation of the hypothesis, not n. So you've got if m, then not n. Excuse me, not if m, then not n. But you've got given the hypothesis not n, you're allowed to now assert not n because of the contradiction in 6, 7, negation introduction, and consequently n by 8 in negation elimination. So that means you've got if m, then n, right? So you've got your first of the 2 sort of subordinate conditionals. Now what do you want to do? Now you want to show if n, then n. Well, that's easy. You know how to do that. Okay, so we've got if n, then n. And so now, drop a line there, right? So now we've got these 2. So we've got if m, then n, and we've got if n, then n. And so because of that, we can now say n, right? But notice, right, this is n, not for here. You might think, oh, good, great, we're done, right? No, you got a lot of hypotheses waiting up here, right? You've got n as a result of having hypothesized m or n. So now what you've actually done here is you've proven this conditional, m or n, then n, okay? And that was the first one you wanted to do, right? You wanted to do m or n, then n. That's yucky. Right? You wanted to prove m or n, then n, but you still need to prove if s, then n, right? So now you're just going to go back and do that. We've demonstrated if m or n, then n. Now we're going to hypothesize s. And what are we trying to do? We're trying to get n. Again, once again, n is not being handed to us. So we just go ahead and hypothesize not n for, actually, this is a mistake. That should say just negation introduction, right? For negation introduction. And we've got not n and n, so the same move. Notice this n is not behind the blue bar. Kind of looks like it is, but it's not, right? So we've got n and not n. So now we can write not n by 16 through 17, negation introduction, which allows us to assert n, and once again, if s, then n, right? So we've got if s, then n. We've got m or n, then n. We've got both of these. And so as a result, we can now write, again, n. But here, right, that's not just the same as having said it here or having said it here. It's because we have actually demonstrated, right, on the basis of 1 and 14 and 20, right, that n. So from m or n or s, we have derived n on the basis of these two original hypotheses, not s or not m, which we now have to discharge. So we discharge the first one, if not m, then n, like that, right? And we discharge the second one, if not s, then not m, then n, and that is exactly what we were trying to prove. Okay? So that is a big who's your daddy. We are done with this. Hopefully this made some sense. Please, please, please take the time to get good at these particular proofs, being able to reproduce them all. If you can, you should feel really good about your current level of understanding in this class.